Okay, welcome back. Let's continue. So let's now go through the algorithms that sort of combined or that are called Davis Putnam. Before we can go into the algorithm of finding efficiently, effectively a model very fast, I want to remind you about the normal form that is often used for this kind of reasoning to simplify the representation of the proofs and the representation of the programming as you want. The one that you find most often for these logics, propositional logic or first order logic, is the closed normal form. I believe you have seen conjunctive normal form and disjunctive normal form in logic in sets. Closed normal form is another name for conjunctive normal form, and basically a propositional logic formula is in closed normal form if it's a conjunction of disjunctions of literals. A literal is an atom or a negated atom, and so we put those together in disjunction of literals, and those again we put together in sets of clauses. So a disjunction of the literals is called a clause, and then a conjunction of those clauses is called a clause set. And basically what you have, if you think in terms of implementation, you would write down a formula in closed normal form as a set of sets of literals. Yes?
What's an atom?
An atom is a propositional letter.
Oh.
Sorry, yeah. And using the term atom is useful when you go to other languages. In first order logic, an atom could be a function or has a different notation. But in propositional logic, it's just the propositions which are the atomic elements of the language. And if you combine the atomic elements of the language with a negation, then this gives you a literal, so either a negated atom or an atom itself. And these are then the smallest elements of your proofs. So if you have a formula which is A or B and not A or C and not B or C, then you would put it into closed normal. This is in conjunctive normal form, in closed normal form, and this is then usually abbreviated like this. And that has a good reason, because if you think implementation-wise, you do not want to start doing any parsing or look on the data structure level of a formula, but you want the simple data structures of a list, for example. And this is far more easy to implement if you think in terms of lists or sets of sets and so forth. Yeah?
How does the or versus A or B, how can you find the list or sublist?
I need to know that it is in closed normal form. And then, because of course there is no difference between those two commas, but I know that this comma stands between clauses, so it is conjunctively interpreted, and this one stands between literals, so it is disjunctively interpreted. It's just a sort of it's unambiguously defined, because you will never see a conjunctive comma, as I would call it, within a clause. Sort of everything you find in a clause is disjunctive, and everything you find in a clause set, these two, is defined conjunctively. And it's just an abbreviation. It's a one-to-one translation between the two syntaxes of formulae in closed normal form, which is far more efficient to program in than this form. That's all. That's all the difference. And it might be a bit confusing in the beginning, but it really isn't. So whenever you see a clause, then it's a disjunction. Whenever you see a set of clauses, they are combined conjunctively. You can check it on this slide and you will always understand it. Yeah. So now the question is, of course, how do we get a formula into closed normal form? And I'm not sure whether you've seen it, but it's relatively simple. You have a set of rules, 5 rules, and if you apply those rules in the order that they're written down here, you will always end up in closed normal form. So if you have a formula in that is on the top level as an equivalence, you have to start with this. You always have to start with the top level, and the top level is if it's an equivalence, then you replace every equivalence with two implications, both directions. If you have an implication, you replace the formula with non-A or B, or non-alpha and beta, which is just the logical equivalent for the implication. So it really is a rewriting algorithm here. You take the formula out of your set, out of your formula, and you replace it by one more formula, one other formula. First you do the equivalence, then you do the implication, then you move the negation inwards, because we want the negation always be on the atomic level, so we need to bring it inside this rule. So if you have a negation of a disjunction, you take the negation inside to the two partial formulae, and you change the operator from a disjunction to a conjunction, and here you do the opposite. You change from conjunction to disjunction if you have a negate. All these formulae are equivalent, so it's an equivalence rewriting, so nothing changes in terms of the meaning of the formulae. It's just that the structure changes and that you get a more easily processable set of formulae. Then you have the Morgan rule, which moves conjunctions outward. So if you have a gamma or and then a conjunction, you just apply the disjunction to both of the conjuncts, and you conjoin the two formulae, and then you split the conjunctive clauses into the set format that we have. Yeah? So it's a very simple procedure, and if you want to, we can give you the rules in the exam, so you don't have to learn them by heart, but it's good if you practice with them so that you will be able to transform formula into closed normal form. So here's an example from our game again. So we have the formula B11 is equivalent to the disjunction of P12 and P21. We eliminate, because we have an equivalence, we eliminate the equivalence by replacing it with the implications in both directions. Which was the first of the rules, as you remember. This is just a rewriting of the things. Then we eliminate the implication with the formula that alpha implies beta, replaced by not alpha or beta. So that was rule number 2. Then we move the negation inwards using the Morgan's rule. So we had what's happening now? My screen is doing weird things again. When it wakes up. And I have no idea what happened to the video. Okay, so maybe we have a video or we do not have a video from the moment. So here was the moment where we moved the negation inward. So we had this negation for a disjunction, and it turns into a literal now, the negated atom, and the conjunction here. And then we apply the distributed distributivity law, conjunction over disjunction, and flatten the formula into closed normal form. Yeah? I think this should be rather familiar for most of you, and if you haven't seen this before, or if you've forgotten, just practice it and it will come back. It's really an easy, simple application of the rules. And in the interest of time, I will also skip that, because it would be exactly the same, and I think it's more important to spend more time on the core algorithm of Davis-Putnam. So if you want to practice it at home, and in the exercise, there's also, on Friday, there's one exercise where you can practice. So the big switch of Davis-Putnam in the first stage was that now they didn't look through the truth table the whole row anymore, but they started with a partial assignment. So the PA starts for partial assignment. And so basically you start out with a minimal partial assignment, and you just say, okay, I assign a value for one variable, true or false, whatever, and then I check whether my clauses become true or whether they maybe become false. And if nothing happens, if my knowledge base doesn't become inconsistent or proven to be I found a model, then I just continue with assigning a new value to a new variable. If you think in terms of state space search, we have a state which starts with an empty assignment. We have n choices for assigning value true to our n variables. We have another n choices assigning value false to our n variables. And that gives us sort of a search tree of 2n breadth. And then we can just continue with a depth first search in order to find a model. Yeah? And the algorithm here, it means this is a stopping condition. If the formula alpha, we're now looking again at satisfiability of the formula alpha. If alpha becomes false, given a partial assignment, then I return false, so I'm unsatisfiable. If it makes the formula completely true, if I know that it's now true, then I can return true, and otherwise I have to choose another proposition that occurs in the formula alpha, and I just call the procedure recursively with the assignment of one value. For example, I assign the value false to the proposition P, and then if this is true, then I return true, and if it's false, then I return false. So how does it work? So suppose that I have this set of clauses. How does the algorithm work? You start with choosing, in this case alphabetically, a variable alpha, and you assign the value false to this variable. Okay, so nothing happens because the formula is you don't know whether it's true or false, our clause set here. So we have to go into the recursion and assign a value to the next variable. The next variable is b, and we assign the value false. So that is in red. We assign the value false. Again, we don't know anything. None of them become true. None of them become false, none of the clauses. Because the whole formula would become false if one of the clauses become false. And it would become true if all the clauses become true. So that's the notion if you have a conjunction of disjunction. So again, now we have to assign a value c. Again, we choose the as a false. And of course, now the first clause becomes wrong. Yeah, so it's false. Because we have to say that false, false, and false. So this one then cannot be satisfied. Okay, contradiction. We do the backtracking. Now we assign the value true to C, yeah? Because we had assigned the value false to C. Now we do the true to C. But now the third clause becomes wrong. False, sorry, I should say false. Yeah? Okay, so that means that the choice of B being false was a wrong choice. So we have to do backtracking. But now choosing B to be true also shows us that this assignment makes the formula false. Yeah, because of the second one now becomes false. So we have to do backtracking again. We have to go to A and assume that A is true. So if A is true, okay, nothing, we don't know anything yet. Now we suppose B is false. We always start with false if we have a choice. B is false. We don't know anything yet. We choose C to be false, but that's a contradiction with respect to the last clause. So we have make this one false. So we have to do the backtracking. We suppose it is now C is true, and then we found partial assignments for our variables, which make all of those true. Yeah. And after 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, we find them all. That was the original algorithm of Davis Putnam, I think from 61 or so, yeah, which basically is, as you see, a depth-first search algorithm through the possible assignments of values to variables. But now this was still rather inefficient, and there are a number of tricks that you can apply, and those are the ones that helped in the first instance to improve the algorithm a lot. And so one thing is to start early with finding contradictions. So basically, these are two general rules that you have in order to stop your search. If a literal L is true, then the clause becomes true. So you can simplify your clause set. And if a clause C is true, then you can just leave out the clause itself from your clause set. So now we start by doing those two things. We start to manipulate the clause set while we're doing the search. That's a very important one. Yeah. So what it means is that it's okay to delete clauses if they contain a true literal. And it's okay, so that is the second one, is now that it's okay to shorten clauses that contain a false literal. And then, if a literal L is false, then the clause that only contains this clause is false, then the empty clause means false. Okay, so these are the three steps. We can delete the clause that contains a true literal, and we can shorten one which contains a false one. Okay, let's see how this turns into the algorithm. It's the same algorithm as before. So here we have the stopping conditions, here we have the recursion, and then we have the two ideas at the beginning: remove clauses from alpha containing literals and shorten clauses that contain the negation of the literal. How does it work out with our algorithm again in practice? So we start out again with A, assign the value false to A, and then we can change the set of clauses. According to the assumption that A is false, we can shorten the first one, because here there was an A. A is false, so we can delete the A. A is false, so we can delete the A. A was false, so we can delete the A here. And here, A was false, and we have not A here, so that makes this thing true, so we can delete the whole clause. These are the two operations. Shorten when you have a negation of the literal in the clause, and delete the clause if you have the clause, the literal itself in your clause. This already is quite an improvement, because now we have a far easier way for our search. So this A was supposed to be wrong, so false, so we continue with B. B now false means that we can sort of delete B from the first one, and the second one also disappears. And now we apply C is false, and we get our contradiction. Of course, we get the same contradiction. Now the first one becomes empty, is the empty clause, so we lose. We have to do the backtracking. Now we violate the third one. We do the backtracking again, and we do the search again. Now suppose A is true, then we get the three first, we can delete those. because A is the same literal as the one that now gets the A value. And we can delete it from here. And so we can jump immediately to C being true. And if we do this systematic going through the algorithm, through all the options again, always choose alphabetically, negate it, and so forth, if that was our algorithm, then we would have to do this step as well fully down here. This already helps us to do the decisions here on the clauses, but you have already seen that why on earth go through the B up here? So we can do better, and that was also recognized in the literature in the years when the algorithm was developed. And there comes another improvement, and this is the one that really changed. It's a game changer and made it more really efficient enough to deal with many huge problems. And the first one is a branch immediately on unit literals. So if you have a clause that only contains one literal, take this one and start with this literal. So now we start ordering the literals. Another thing that you should do is branch immediately on pure literals. What are pure literals? Pure literals are the ones that occur either without negation in all the clauses or with negation in all the clauses. So you don't have a alpha and not alpha somewhere in your clause set. You only have alpha and alpha, or not alpha or not alpha and not alpha. Yeah. So these are the two main concepts. The unit clauses are the ones which only have one literal, and the pure literals are the ones that occur in different clauses but with the same polarity, as it's called. Yeah. And these are the ones that you should start with. The first one actually being the unit literals. This really makes it efficient. And then we see the algorithm again, and that's now the real Davis-Putnam algorithm, and that is you do the simplification of the clauses. So you remove the clauses which have the literal themselves, you shorten the ones which have the negation of the literal, then you do the start-stop condition, and then you start doing the procedure on the unit or the pure rules first, literals first. So let's see now how this works out in our algorithm for real. Again, we would start with in this case, alphabetically in our implementation, because we don't have any unit clause yet, and no pure literal either, because A occurs here positively without negation, but here negative. Here, B occurs positive, negative, C occurs positive and negative, so we don't have any pure ones, we don't have any literal, any unit clauses, so we have to do the standard procedure. Okay, now we simplify our clause set again, and now we have actually unit clauses. Yeah. And of course, if you have a unit clause, you know that you have to choose the value that makes this unit clause true, otherwise it doesn't make any sense. So now you have to choose B to be false. Okay, so we do that. Now we have one unit clause here, and one unit clause here. Doesn't matter which one you choose, you get to a contradiction immediately. You have to do the backtracking, but now we choose the A here to be true. What happens when you choose the A to be true is that the first three disappear, the second one becomes a unit clause, and you have to start on the unit clause, so you choose C to be true, and you find the solution. And basically, we have now reduced the search space from 9 nodes that we had on the beginning to 1, 2, 3, 4, 5, 6. So quite a significant reduction of the search space. So remember that the core ingredients are whenever you decide on a literal, all the clauses in which the literal appear with the same polarity disappear, and the ones where it appears with a negative one, you can take it off the clause set. And that every step of the recursion of your procedure, your clause set becomes significantly more shorter and smaller. with shorter length clauses. And if you choose the ones with unit clauses, the one which only have one literal, then you really reduce your search space a lot. So that's the one to start with, and the same holds for the pure ones, because they also reduce the number of clauses a lot. And then, of course, the question is, we now started with the A, and why on earth would you start with the A? There's no reason apart from the fact that when you parse your formula, you have by coincidence, you have a literal in the first position in the list. Doesn't make any sense. Or alphabetically. From a computer perspective, from an algorithmic perspective, doesn't make any sense either. Yeah? So the question is, can we think of a good way of decide which literal to start with and which value to give it, whether true or false? And of course, this is where the heuristics come into play from last week. Let us now decide on the first path to explore by some knowledge we know about the processes. And the idea is that you use the ones that identify the most constrained variable. So the one that helps you reduce the size of the clause set in your process as much as possible. The first one, which is a kind of heuristics as well, is that you do the unit clauses first. But now we talk about the non-unit clauses and the variables we have. And the idea is, for example, one heuristic, there are more, and there's a lot of research being done in that field. One simple one is MOMS heuristics. So you look at the most occurrences in clauses of minimum length. So you first take the one with the minimum length, and then you just check which of the literals occur most, or the atoms, sorry, which of the atoms occur most often in these clauses of minimum length, and that's the one you start. Yeah. So before we spend maybe some more minutes on practicing this algorithm, to wrap up. So it was invented in the 60s, as I said, and in the first years, so they could deal with hundreds of variables, which is already quite impressive. Remember, we had 7 variables in our truth table, and that was quite difficult already to see. And now if you have 300s, and in the turn of the millennium, this really went far above 1,000 of propositions. And in the, so for some problems, for example, in hardware verification, you could really represent problems with millions of variables just by having this very clever algorithm. So let's look at an example and take a bit of time to play with this. I think we have enough time to calculate this example. So if you want a piece of paper and play around with it yourself, and then we do. I have 3 variants. The first variant is a simple one without any heuristics. And let's do the alphabetic ordering, and let's do false first, precisely as we have seen on the slide. And let's take this example, Q or not R or not P. Take a couple of minutes, and then I'll try to explain it on the board, or we do it together on the board. Okay, I see many of you trying, so but in the interest of time, let's do it centrally for the second or third steps. So, as I said, start alphabetic first. So we have a PQR. So we start with P, and we set it to be false. Yeah. So what happens to the set of clauses? So what happened to the first clause? P is true. Remember the two things. I could either delete the clause if the literal was true, or I could delete the literal if it was false. You can also, I mean, if you forget this, you can also just think, if you want to satisfy the constraint that Q or not R or not P, and you know that P is false, what happens to your constraint? It's satisfied, because the first bit, because the not P is true. Yeah? The not P is true because the P is false. So you have something which says not R or so, or Q, or true. Of course, you choose for the true. So the first clause disappears. What happens to the second one? We know that P is false. So we know that the second part of the second clause is not satisfied. This one is not satisfied. So we can just retain the other two. That's not R or Q. Sorry for that. What happened to the third one? Just stays as it is. R or Q. The last one. What happened to the last one? Just minus Q. Yeah. Okay. What's the next step? Sorry, I should go. What's the next step? R false. Why R false? Yeah, but we do have a unit clause rule, which is sort of has priority. And we have a unit clause. This is a unit clause. Welcome. So the next thing we do is that we decide. I'm really sorry about this. I have no idea what to take an old one. Okay. So we take Q as our new atom, and we take the negation again, false. Yeah. Because this is the only way of satisfying this one is to make Q false. Yeah? Okay, so how does our clause set transform now? I shorten the first two, so I get not R as one clause. R the next clause, not Q goes. So these are the two left. Yeah? So now I see choosing either of them makes it unsatisfiable. So we're done. So I can do not R here, but I don't have to look further. So neither of them will be able to become true. So we have to do the backtracking. Backtracking is that we have to decide on Q to be something else, but that doesn't make sense because it was a unit clause rule. So we don't have to do any backtracking. So we go back to the P. We have to do the backtracking on the P and now decide to be true. What happened to our clause set up there? So P is true, so we have to keep the first one, you say? Yeah, so we get Q or not R. And what happened to the second one? It goes. Third one stays. R or Q. Okay. What happened to the third one? Sorry. third one disappears. Yeah. Okay, which rule are we applying now? What comes next? Q comes first. Why? Alphabetic? Pure. Pure goes first. It's pure because it occurs only positively. Yeah? So we have a R to go here. And we'll make it true. And we're done. Because now, choosing it to be true, we can just delete all the clauses. Yeah? So we found this should have been a P is true and Q is true. So we found a partial assignment that makes all the formulae true. Yeah? Okay. So that was sort of the non-informed way of doing things. Now let's look at the second variant, which is using the Mom's heuristics. Most often in the clauses of minimal size. So what do we start with? Yeah, Q. Why?
Every clause has a Q in it.
Yeah, but that is sort of the wrong answer to the right. Sorry, the right answer, but in the wrong way. So we are looking at the minimal clauses. Which are the minimal clauses? Of length 2. So the 2 to the right. Yeah. So we only look at the minimal clauses. And you're right, of course, that Q occurs there most often. It also occurs most often in the longest clauses. If you had a different one, but in this case, so that would, of course, be a different heuristics if you say you just take the most occurring one. That could also be the case. But here, this heuristic goes one step further, and it chooses the one with the smallest length. And that is, of course, useful because then you allow, the chance that you end up with unit clauses is very high. Yeah, so that's why it's good to start with the ones with the minimal length. So now we look at the 2 with the minimal length. Q occurs most often because it occurs twice. So then we say, okay, we start with Q, and it's we still have we start with false. We haven't thought about that. We have no heuristics for that. So Q is false. What happened to our set? Yeah, so we get non-R or not P, we get non-R or P, and we get R. Yeah, what's the next one? R, because we have a unit clause, so we do R false. Oh no, R has to be true, of course. Let's try like this. Yeah. So then we can delete this one and these 2 bits, and we end up with a contradiction. So this one closes again. So we have to do the backtracking on the Q. And then you see that the first 3 disappear, and all we get here is P, and we find a solution for P to be true. So Q is true and P is true, makes the partial model. Yeah? Sorry, say it again.
Why did you not write down the last clause in this 3 clause already left?
Because I choose Q to be false. So and if Q is false, then the last clause disappears because it is satisfied automatically. Yeah? So it's always if you have the literal in the clause, you can delete the clause. Yeah.
And you choose R is true because the minimal clause is on.
Yeah, because for unit clause, you always choose the one that makes this unit clause true, because otherwise, I mean, if you implement it in a dumb way, you would start with, but then you would automatically get the empty clause. So you can save this step by always starting with the one with the empty clause. Okay, so that is variant 2. That's already faster than without the heuristics. And then if you add one more element of heuristics, and that is, why in God's name did I start here with false? that was stupid of me to start with false, because then I went into the contradiction here. So let's get back this one step. And now do the MOM heuristics that we applied before, but now also look at whether the most occurring literal occurs more often negated or non-negated. So we start with, based on the MOM heuristics, we start with Q again. Q, because that was the one that occurs most often in these two on the right-hand side. And now do we start negated or positive, positive or negative, with a negation or without. Q occurs 3 times positively. So let's start positively, because then we can get rid of many clauses. Yeah, so then we start the one that occurs most often. Q is true. And then we just have the P over, and we can immediately choose the P to be true. And we're done. We found the model. So now we've reduced this whole thing from a quite complex search tree with a bit of heuristics to just the one leaf, the one branch that gets us immediately to the partial model. Yeah.
How in the BAM break ties, there's an example of
That's a very good question. How do you break ties? So I just gave you an example of some heuristics, and it's a very it's a straightforward. If you really implement Davis-Putnam, the way they did it in CJAF and in all the more competitive SAT solvers, there is of course far more, and then you have to deal with tie breaking. And I must admit that this heuristics I thought of in order to make the example more interesting so that it would work. I have no idea whether this makes sense if you really have a proper system. So what you do is, on the one hand, you try to understand what are the theoretical properties of such heuristics, but then you also run experiments just seeing which one is faster. And the same holds for tie breaking. So sometimes you just say you do randomly, and otherwise you implement some other heuristics on top of that. Yeah. So that was Davis-Putnam's algorithm, and the summary is that it is useful if you have formulae in closed normal form. You can show entailment by refutation. So basically, you show entailment if you add the negation of the formula and you show that it's unsatisfiable. It has a worst case complexity of 1.61h to the power of n. Remember, we had truth tables, we had 2 to the power of n, and now we don't, unfortunately, we cannot reduce the exponential factor, but what we can do is reduce the factor on which it is applied, and that makes a huge difference. So if you have 50 variables, we have an incredibly huge number of states that we have to look into, the search space in the worst case, and if you reduce the base here, then it becomes far more easy to handle. So, so remember the properties of the algorithms that we wanted to have for logical calculi. We wanted them to be sound. That means that if something is entailed, if something is proven, it must be entailed. We want them to be complete, so if something is entailed, we want it to be proven, and we want it to terminate. And then a logic is decidable if there is such an algorithm that is sound, complete, and terminates. And we can show for Davis-Putnam that it is sound, it is complete, and it terminates. So these are proofs that are relatively simple. It only shows unsatisfiability. So to show that you can use the Davis-Putnam for entailment needs some kind of transformation, but that's relatively straightforward. What remains, and that is what you've seen on the previous slide, it remains exponential algorithm. So you still have the power of the number of variables, and there's nothing we can do about it unless the famous NP problem is solved and someone shows us an algorithm to transform these problems into polynomial, which nobody believes. that can happen. So it can still take exponential time, and that's why people have also looked into approximation of these algorithms. So this was an algorithm that tries to find models as quickly as possible. So that is very much appropriate if you think that there are some models, yeah? Because if there are many models, it's easier to find one. If you want to show unsatisfiability, so you have, for example, an assumption that your formula is really entailed, then this algorithm might not be the best one. And then you might want to use a different algorithm, but for example, by manipulating the formulas themselves. And we're looking tomorrow into another algorithm, so a different paradigm of reasoning algorithm, and to see how you can achieve exactly the same satisfiability on propositional clause normal form, but with a completely different algorithm. And that's sort of the task for tomorrow. And I think for today we're done. Thank you.